Hello, in this lecture we will discuss the AC voltage applied to a capacitor. This figure shows an AC source of EMF E connected to a capacitor. It is a purely capacitive circuit. When the capacitor is connected to the AC source, it alternately charged and discharged as the current reverses each half cycle. Let Q be the charge on the capacitor at any instant of time t. Then the voltage across the capacitor is given as Q upon C. We know the relation that the C is equal to Q upon V. So V is equal to Q upon C, or Q is equal to C into V. Replace the E by E naught sine omega t. As you know, that is the current is rate of flow of charge. So to find the relation of the current, we have to differentiate this equation. Now when we differentiate the sine omega t, you know it is equal to cos omega t. So this relation becomes C omega E naught cos omega t, and this C omega can be written as 1 by C omega. So I is equal to E naught cos omega t 1 upon C omega. This 1 upon C omega is equal to the capacitive reactance, and E naught upon 1 by C omega is replaced by I naught. So it is the equation of the current. Now I naught is equal to E naught upon 1 by C omega. This 1 upon C omega is represented as Xc, which is called capacitive reactance. It is the capacitive reactance, and it plays the same role in the AC circuit as the resistance placed in resistive circuit. As it plays the same role as the resistance plays, so its unit is same, that is ohm. When we compare this equation number 1 and equation number 2, then there is a difference of pi by 2. It means the current leads the voltage by the angle of pi by 2 in pure capacitive circuit. Now, let us see the waveforms. As in the case of the capacitive circuit, current leads the voltage. So when we look at the time, the current acquires the maximum value earlier than the voltage. In terms of the phasor diagram, it is the EMF and the current leads the voltage, so it should be in the second quadrant. The angle between the current and voltage is 90 degrees. So it is the phasor diagram of the AC circuit with a pure capacitor. Now the inductive reactance. As already I told you, inductive reactance is represented by XL, and which is equal to omega L. Omega is 2 pi n, where n is the frequency. It means the inductive reactance is directly proportional to the frequency. For the DC circuits, the frequency is equal to 0. It means inductive reactance for the DC circuit is equals to 0. It means to say that inductor does not obstruct the current in case of the DCs. And in case of AC, higher is the frequency, higher is the resistance or the inductive reactance. When we plot a graph between the inductive reactance and the frequency, then it will be a straight line passing through the origin. Now the capacitive reactance, as you know, the capacitive reactance is given as E naught upon Xc, and Xc is equal to 1 upon C omega. This Xc is called the capacitive reactance. Omega, again it is equal to 2 pi n. So Xc is equal to 1 upon 2 pi Nc. Or we can say that the capacitive reactance is inversely proportional to the frequency. For DC circuits, frequency of the DC is equal to 0. It means capacitive reactance equals to infinite. Hence, we can see that the capacitor blocks the DC. And in case of AC, higher is the frequency, lower is the capacitive reactance. So when we plot a graph between the capacitive reactance and the frequency, then this will be the shape of the graph. Thank you and have a nice day.